homework up here. And I'll scrub this, and we can start our material today with the solution to number 4. Okay, so let's work problem 4. It went KHG, right? So we didn't prove it, but when a group lives in a group, it has to be a subgroup. And it has to share the same identity because otherwise G would have 2 identities, etc. So K is a subgroup of H is a subgroup of G, and naturally, because every element in K lives in G, K is also a subgroup of G directly, right? Well, indirectly, but yeah. So this is a chain of subgroups. So let's define some things to get this problem done. It's not that hard if you look at it this way. Let's define the size of the group K to be K. And the size of the group H to be H. And the size of the group G to be G. Then we have a rule for the size of the indices, right? By Lagrange's theorem. Says that the order of G must equal the, let's do H as the subgroup, right? Must be the index times the size, right? Because when I do cosets, what do cosets do to a group? Break it up into cosets break up a group into we're here on Monday, right? Cosets break up a group into what? Chunks of
they all are equal size?
Yeah, chunks of equal size, right? So I have this many copies of chunks that big, right? That's what Lagrange's theorem means. Because all the cosets of H have the same size as H, and the index is nothing more but a count of how many cosets there are. So that's going to help us. So right away we know that the order of G can also be written how then? Well, it can be written as the index of H in G times H, right? That's what I called it. But by the same theorem, by Lagrange's theorem, applied to groups of finite size, H must equal what? Size of this group, applying the same theorem to H and K, must be what? Index in H of K times K. Right? So you got to go from here. So So let's give these letters. Let's call this one N, and let's call this one M. Then what do we have? We have that the size of G is actually M times H, right? But what's H actually?
N.
N times K.
So now, continuing our line of argument, what must be, if I rank G in terms of the direct subgroup relation with K, it must be the index of G, of K and G, times what size? K is a subgroup of G, so I can do this, right? So by Lagrange, what size goes here?
K.
Little k, right? But what's all this equal to? The size of G is equal to M N K. So cancel the k's, and the size, the index here must equal M N, but what's M N? It's those other indices, right? So this is just, don't get confused by the symbols, this is just arithmetic of integers, right? That's some number, that's the size, this is some number, that's how many cosets, and the product is the size of the group, because H breaks up G into that many copies, which is, because all the cosets have that same size. So that's a theorem that really summarizes Lagrange's theorem well. And you just start assigning letters to these things, that just makes sense to do the arithmetic that way. Okay, that was number 4. So let's move on to normal subgroups, the definition and some examples. The motivation for normal subgroups get some more color to see how the markers behave today. We want to be able to do arithmetic on our cosets as follows. I want GH, group operated, that's my arithmetic, the group operator, with KH. I want this to happen. But it turns out this definition of how to do arithmetic of cosets will fail. If the left and right cosets are not the same thing. Because what I really do to do this is I essentially commute this to be its left, its right coset, so G and H are together. I multiply G and H and I commute the whole thing again. I actually prove that I can get to here. I have to turn this around twice to prove this, and that'll only work if left and right cosets are equal to each other. Well, remember what a coset is. That's the definition of my right and left cosets. What's one case where it's obvious that those will be the same thing? One condition on the group G. Well, obviously these two things are the same if I get the same answer here and here every time, right? What does that mean? No, because it has to work for all of them, right?
If your operator is commutative.
So it must be what kind of group?
Abelian.
Abelian, right? This always works. Because G1, G2 is equal to G2, G1, right, for all G1, G2 in the group. If it's abelian, right, everything commutes. So not only are these two sets the same set, but they're the same element by element because GH is equal to HG in an abelian group. But this is a weaker condition than that in two ways. You see why this is this condition is not as strong, not as restrictive as abelian. There's two particular ways. This is not quite as tough as demanding this group's abelian. If the group's abelian, this always works. That will always be true. But can you see something a little tough, less tough in this definition than abelian? I guess first question is, does this element G have to commute with every element in the group? Or the elements of H, right? So it doesn't have to commute with everybody, just the elements of H. And we saw yesterday, well, last time we were together, we had two permutations. We had a set of permutations. I believe there was 4 of them, where we multiplied a permutation over here and got a set, and we multiplied a permutation on the other side. Same permutation on the other side, and we got the same set, but remember, element by element, it wasn't the same. Right? That was what we had on the board. So I multiplied this element through by these elements, and I got one particular set. I multiplied on the other side, that is sigma 1 row, etc., and I got the same set, but not in the same order. I produced actually different answers at every stage. I'll bring that back up later. So that's the other thing here is I don't demand at all that GH equals HG. I only demand that I build the same set, and that's a weaker condition that way too. So the abelian case is trivial, so let's just get an abelian case on the board one more time. And then so what's a nice simple abelian case that's a little different? How about a set of all 2 by 2 matrices? If I use them all, and I want an abelian group, what's my operator? be, I want to use every 2 by 2 matrix, and I want the result to be abelian. What must be the operator? Can I use matrix multiplication?
But.
No, why not? That's right, why not? Is matrix multiplication, is that a commutative operator? No. And is every matrix invertible? No. Not under multiplication. So I'm going to call this set M, and with matrix addition. That's obviously an abelian group, right? Because the 0 matrix is going to be my identity, right? All zeros. So 0, 0, 0, 0 is going to be my identity matrix for addition, right? Obviously, if I add any 2 by 2 matrices, I get a 2 by 2 matrix, so it's closed for sure. What it amounts to is adding 2 real numbers, right, in each position. So closure's easy. What's the additive inverse of this matrix? A, B, C, D plus negative A, negative B, negative C, negative D, where those are the additive inverses. That gives me my identity matrix, right? My additive identity matrix. I'm not calling it I, because that would be confusing with the multiplicative identity matrix. And what else do we need to be a group?
Closure.
Need what?
Closure.
We have it, right? We said that. Associativity. But we'll just say that matrix addition is associative. It is. Because I add element by element. I essentially inherit the associativity from the associativity of addition in R. Because I'm not doing anything strange. Matrix multiplication is a lot harder to show that, but matrix addition is really, I get associativity just like I do for vectors. So that's a group. This is an abelian group. Can you think of a subgroup of this? How can I make a subgroup that's not all of these? Remember adding matrices. I think we looked at this before. Anybody think of something that would look like a subgroup? Closed, identity, and inverses, right? All I need. Let's try to define H as some set of 2 by 2 matrices that is not all of those.
Can you just do A, B, and C are integers? A, B, C, and D are integers.
Ooh, I like that. Yeah. That's a really nice one. Yeah. If I add integers, I get integers, right? 0 is an integer. So it's closed, and associativity is always free in the subgroup. So I get that for free. This is an abelian group, so I know that H is normal. Automatically. That is, if I take any real number, any other matrix, right? I form these by taking things in the outside world. So I'm going to take from U plus H, right? That's how I form cosets. In this case, I take an arbitrary element of the group, and I add because that's my group operator, right? That's going to be the same clearly as because when I take each element by element, it's going to work. I take one of these, which is real entries, and add it to one of these. I'm going to get, what's it going to look like? It's going to look like R plus A, B plus S. Well, T if I want to be technical. T plus C and U plus D. Right? As I take a typical matrix in here where RSTU are reals and those are integers, right? But that's clearly the same as going the other way because real addition commutes. But I don't even have to prove that, because I know this is an abelian group. To start with, every subgroup is normal. So this is, I can prove it, but I don't need to. I know it's normal simply by the fact that because M is abelian. Let's stop the tape there.